Hello friends, welcome to my channel. Let's have a look at today's daily challenge problem. Problem 64, minimum pass sum. In this video, we're going to explain a solution based on dynamic programming. So this problem is actually a routine problem or a typical example of dynamic programming. First, I'll look at the problem statement, and then we do the analysis and share the code and explain line by line. So in this problem, we are given a m by n grid filled with non-negative numbers. So we would like to find a path from top left to bottom right, which minimizes the sum of all numbers along its path. So here is a note. We can only move either down or right at any point in time. So here are two examples, and let's look at the first example with some detail. So in this one, the output is 7. So if we along the top row and then the last column, so we're going to get this sum. So if you try other ones, for example this one, so you're getting 1 plus 1 plus 4, that is 6, then plus 2, that's already 8, larger than 7, right? So the constraints or additional assumptions for this problem are the following. First, m and n are the number of rows and number of columns. They are both bounded above by 200. So this 200 bound for m and n basically gives us the problem size. And the grid value is in between 0 and 100. So here the assumption that the elements in the grid are non-negative actually is an essential one or important one. So because it's non-negative, right, even we do not have this assumption, so we'd better not to go back and forth, because this way it's going to increase the total sum. So, but the problem also emphasizes that we can only move down or right. So with that said, we are ready to look at the analysis. So in this problem, first let's look at the key assumptions. So the first one is that each cell contains non-negative numbers. So we have explained, right? So we cannot move back and forth, even we do not have the assumption that we can or restriction that we can only move downwards or rightwards. The second one emphasizes this fact, so we can move only down or right. So this is an explicit assumption. So the above assumptions, in particular item 2 here, makes it very easy to set the first row and the first column in the DP table. Because if we are in the first row, if we want to move towards the right, we can only move towards the right. And if we are in the first column, so we can move downwards only. So in this problem, we are going to use a 2D dynamic programming table, so DPIG. So the interpretation is that, so this DPIG means minimal pass sum ending at the cell or coordinates IG. And then the DP update rule is very straightforward. So DPIG basically equals grid IG plus minimum of DPI minus 1G plus DPIG minus 1. So DPI minus 1G plus grid IG means that we're going to from I minus 1 and G then downwards to IG. And the DPI G minus 1 plus grid IG means that we're going to move right from I G minus 1 to IG, right? So we take the minimal of the two options. So with that said, we are ready to do the coding. First, in version 1, so I'm going to use some extra space, and in version 2, I'm going to do it in place. So first, with extra space, so we just want to isolate the main point. So here I'm going to introduce m and n. So it's grid and length grid 0. So here m and n are the number of rows and number of columns in the grid, And then we are going to make a DP table. So first, this is the number of columns, and then for a dummy index in range m, so this iterates the rows, right? So we have m row and n columns, same for the DP table. And then what we are going to do, first I'm going to set dp00. So this will be the grid 0, 0, right? After that, let's first set the first row and then first column. So we can regard this as a preparation, and then we do the generic element. So in order to set the first row, we're going to iterate. Let's use G for column. So we're going to iterate from 1 to m, right? And then dp0g would be grid 0g plus dp0 g minus 1. It's because we are starting the index g from 1, so g minus 1 is non-negative, therefore it's a valid index. So this is the setting for first row. Now let's look at the first column. So we are going to iterate for I in range 1 to m. Then dpi0, the first column, right, equals grid I0 plus dpi minus 1, 0, right? So again, we are starting I from index 1, so I minus 1 is a valid index. So these two lines actually also indicates that when we want to set dp0g or dpi minus 1, its previous elements is already set. So with that said, we finished the setup for the first row and the first column in the DP table. Next, let's look at the generic element. So for this, we're going to iterate for I in range 1 to m. So m is not inclusive. And for g in range 1 to n, same, 1 is inclusive, while n is not. So then we're going to set dpig, right? So we just need to copy here, right? It's grid ig plus minimum of dpi minus 1g. It means that from I minus 1g move downwards, and this is from I g minus 1 move rightwards toward both ending at ig. So with that done, so we are ready to do the return. So we are going to return dp. Basically it's m minus 1, n minus 1. So but we can write negative 1, negative 1. The last row and the last column, right? So this is the meaning of negative 1, negative 1. So with that said, let's first do a check. Yeah, it passes one example. Now let's look at generic case. Yeah, it passes all the cases. So first, let's look at the space extra space we used. So here the space is mainly from the DP table, right? So temp complexity is O of m times n, and for space we also have O of m times n, right? Due to the DP table. However, for this problem, so if we observe the pattern and we have the interpretation in mind, so we can improve the space complexity very easily. So let's copy this part, and then let's write the coding in place. So here I'm going to use in place operation. So for this, again, I'm going to get m and n, the number of rows and number of columns. However, I'm going to delete these two lines. And then we're going to set the first row and first column. For this, we're not going to use DP table because we can do it in place. So for this, we can do this. So what we want to set is grid 0g. So we just need to increment this one by grid 0g minus 1. So this is the one. And then similarly, we want to set grid I0. So then we just need to increment to be grid I minus 1, 0. So if we regard the first row as a list, so it's actually we are computing the prefix sum. So similarly for the first column, where we are computing the prefix sum or partial sum. And then for the generic element, so what we are going to do is we change this to be grid ig. And then the increment is nothing but the minimum of the grid values above and leftwards. It's grid, the grid. So then we return the grid, the last element. So this way, so we didn't use extra space. So this way, the space complexity does not change. O of m times n, and the time complexity does not change. O of m times n, but we save a lot of extra space. So with that said, let's test it. Yeah, it passes one test case. Now let's look at the generic case. Yeah, it passes all the cases in a decent, fast fashion. So with that said, that's about it for this specific problem. So this problem is actually a very routine problem for practicing dynamic programming. So if you are interested, you are welcome to follow up our channel in YouTube. So also, if you find the explanation helpful, you are welcome to share or distribute with your friends. With that said, I guess that's it for this video. Thank you.